All right, I'm getting back on the horse here. I figured we could use a solution guide. Okay, hopefully this works out and I remember how to record. Okay, 101, let r of t be a differentiable function that represents the rate at which people leave a restaurant in people per hour, t hours after opening. Okay, that's in the table, that makes sense. What is an approximation of the total number of people who have left the restaurant from t equals 0 to t equals 10 if a left Riemann sum is used with 4 subintervals indicated by the table? Okay, so I'm going to go, this is 2, 2, 3, and 3, which means we have to do individual rectangles. So we're doing left rectangles, and let's see, people per hour times hours. Sounds like we're going to get people. So that's going to be, we're going to do 2 times 2, 4, plus 2 times 4, which is 8, and 3 times 1, 3, and 3 times 8. 24. Okay, so 8 and 24 is 32 plus 7 is 39 people. 102. Let f be a differentiable function, so f is continuous. Selected values of f are given in the table above. What is the estimate of the definite integral from 1 to 17 f of x dx if a midpoint Riemann sum is used with 2 equal length subintervals as indicated by the table? Okay, so notice what it says, 2 equal length subintervals. We can't do midpoint rectangles. I mean, it does tell us 2, but hopefully you understand, to do midpoint rectangles, we have to have a data point between the endpoints. Okay, so what are we going to write? We're going to write 9 minus 1 times f of 5 plus 17 minus 9 times f of 13. So that's 8 times 3, 24, plus 8 times 2, 16, gives us 40. And we were just doing area under the curves. We don't have to divide or anything. Okay. 103, let f be a differentiable function. Selected values of f are given in the table above. What is the estimate of the definite integral from 4 to 11? And I'm just checking that this is indeed 4 to 11. Okay. Using a trapezoidal sum with 3 subintervals indicated by the table. Okay. So that's going to be, I'm just going to do it kind of the long way because that's 3 and 1 and 3. Okay. So 7 minus 4 is the width, times f of 4 plus f of 7 over 2 plus 8 minus 7 times f of 8 plus f of 7 over 2. I'm going to go back and change this first one. I like to have them nice and in order. Okay, and plus 11 minus 8. Can we go a tiny bit bigger? Yeah, okay. 11 minus 8 times f of 11 plus f of 8 all over 2. Okay, f of 7, 1 plus 2 over 2, plus 1 times 4 plus 1 over 2, plus 3 times 3 plus 4 over 2. So I can already tell I'm going to have an extra half in here somewhere. Okay, so that's 9 halves plus 5 halves plus 21 halves. What is that? 14 plus 21, 35 halves, which is 17 and a half. Okay. Let f be a twice differentiable function that is increasing. F prime is greater than 0 and concave down. F double prime is less than 0 on its entire domain. If a finite number of subdivisions are used on the interval, which of these, finite, like we're not doing an integral. Okay, which of these estimates is an under approximation of the true value of the definite integral from a to b? It actually doesn't matter how far apart a and b are, but the farther we get them apart, in fact, I'm going to get a little bit farther to the left. The farther we get them apart, I think the more obvious this will be. Okay, so let's just put a there. Okay, so a left Riemann sum is definitely going to be an under approximation, so that for sure. A right Riemann sum is going to be too much. I don't think I need to draw that for you. And then a trapezoidal sum, this one isn't obvious. The trapezoidal one has to do with concavity. So if you draw in a trapezoid, you can see, even if we just do one, that will be an under approximation, so 1 and 3 only. Ooh, this one I know you're probably going to watch. Okay, so one way to go on these, if we are going to translate to an integral, is to put in I equals 1, I equals 2, I equals 3, and see what terms we get, and then I'll do the kind of shortcutty way. Okay. So if we put in I equals 1, our first term is 3 over n. You know what? Let's make some number of rectangles. Let's say it's a 4. So that'll be 3/4 of 2 plus 3/4 times 1, there's my I, squared. Plus, well, 3/4 is going to be the same. So the reason this helps, let's see, 2 plus 3/4 times 2, squared. Now we're feeling it. Okay, that 3/4 must be the width of each rectangle. Let's see, 2 plus 3/4 times 3 squared, and 3/4 of, what is it? 2 plus 3/4 times 4 squared. So, you could think through this, and obviously this isn't supposed to be 4, but if n were 4, that really tells us a lot. So it tells us the width from left bound to right bound is 3, and that's this 3, that's this 3, and this 3, that's all the same. Because if we had had n equals 4 or n equals 10, that would have worked out. So we know, these all have 0 to 3. Okay, what else is pretty obvious? Well, our function is a squaring function, so there's no way it's c or d. And what are the inputs? Well, the inputs are 2 plus a width some number of times, which means the lower bound is 2 and the upper bound is 5. Maybe you don't need to write out all that terms, but if you're in my class, it makes a whole lot more sense if we do it in a finite way and then just pretend. Okay. 106, let f be a differentiable function. If f of x equals the definite integral from 3 to x of cosine of t minus 3 dt, then f prime of x is, well, this is fundamental theorem. So I'm going to take the derivative of f prime. Over on the right-hand side, I'm taking the derivative of an integral, and this is the easy version, constant to x, so we're going to get cosine of x minus 3. Oh man, easiest one so far. We're going to do a whole bunch of fundamental theorem. F is a differentiable function such that f of x is the definite integral from 1 to 2x of t cubed dt. So I'm going to do f prime of x first. And no matter what, I'm getting something cubed, but we have a chain rule, so that's a 2x here times a 2. So f prime of 1 is 2 times 1 cubed, which is 8, times 2 is 16. Okay, let f be a differentiable function, defined as f of x is the definite integral from 4 to x of t squared dt. On what interval is the graph of f increasing? So let's see. F increases on intervals where f prime is positive. And it looks like f prime x squared is always greater than or equal to 0. So we're going to go negative infinity to infinity. Let g be defined as g of x is the definite integral from 0 to x of 2t minus 4t squared dt. What is the x-coordinate of the point of inflection of the graph of g? So we want g double prime to change signs. G prime of x is equal to 2x minus 4x squared. G double prime of x is equal to 2 minus 8x. 0 equals 2 minus 8x. And 8x equals 2, x equals 1/4. I bet at least one of you writes 4. You know, we really should make a sign chart. I don't need to, simply because g double prime very clearly has different end behaviors, so it's for sure going to change signs at x equals 1/4. But it's probably not a bad idea for most of us to check. We can see negative, positive, concave up, concave down. And I just had a brief interlude doing some triathlon stuff. Okay, all kinds of questions. Oh, sorry, we circled. All right, if the definite integral from 5 to 1 of f of x dx is 2, and the definite integral from 5 to 8 of f of x dx is 3, what's the definite integral from 1 to 8 of f of x plus 2 dx? Okay, so your best bet is to make something that's true. So I'm going to go the definite integral from 1 to 8 of f of x plus 2 dx. That's what we want. And we know that's equal to the integral from 1 to 8 of f of x dx. Plus, a lot of people would just add on 2, but it's not. It's the definite integral from 1 to 8 of 2 dx, which we know is going to be 14. But I need some more space there. So I'm not going to monkey with this left-hand side. It's perfect. And over here, I'm going to change the definite integral from 1 to 8, the definite integral from 1 to 5 of f of x dx, plus the definite integral from 5 to 8 of f of x dx. And then I'm going to go 8 minus 1. Well, maybe I'll just do it this way. Okay, and now I need to rearrange. The definite integral from 5 to 1 is going to be the opposite, so negative version. Plus, I can replace this with 3 and replace this with 16 minus 2 is 14. Okay, so that's going to be negative 2 plus 3 plus 14 is 15. Cool. Let f be a continuous function such that the definite integral from 3 to 5 of f of x dx is 4. The definite integral from 9 to 3 of f of x dx is 5. What is the value of the definite integral from 5 to 9 of f of x dx? Okay, so I'm thinking from 3 to 5 plus 5 to 9 is equal to the definite integral from 3 to 9, and then I'll just rearrange as needed. Okay, so the definite integral from 3 to 5 of f of x dx plus the definite integral from 5 to 9 of f of x dx is equal to the definite integral from 3 to 9 of f of x dx. And I want 5 to 9, so this is going to be a negative 4 plus the integral from 5 to 9 of f of x dx. And then this is going to be, hopefully you're okay with this, negative 5, because the negative integral from 3 to 9 of f of x dx has to be equal to the negative here. Okay, and so we're just going to add 4 so I can do a little bit less work, and I'm going to get negative 1. Okay. Ooh, a graph. The graph of a piecewise linear function g above, evaluate the definite integral from negative 2 to 0. Okay, so this, we're simply asked, oh, of g prime. Gosh darn it, you almost got me. Okay, this is a g of x. Okay, so the integral of g prime is going to be g of 0 minus g of negative 2. And we want the y values here. G of 0 is 0. G of negative 2 is 2. So we actually get negative 2. Careful there. Got to make sure everything matches. Okay, and the last one here. This looks like you can't do it yet, but you can do alpha. The definite integral from 1 to 4 of x plus 3. That's the same as the definite integral from 1 to 4 of x over x, 1, plus the definite, 3 over x. Yeah. Antiderivative of 1 is x. Antiderivative of 3 over x is 3 natural log of the absolute value of x. And we're going to do that from 1 to 4. So 4 plus 3 natural log of 4 minus 1 plus 3 natural log of 1. Natural log of 1 is 0. So that's 4 minus 1 is 3 plus 3 natural log 4. Boom. And I'm pretty sure that's it, because the last couple were things. Nope. Still one more page. Okay. And just know I cut off a few because you guys don't know substitution yet. Okay. F prime of x equals 6x squared plus 2x. F of 2 equals 4. Then f of 1 equals. So this is the other half of the fundamental theorem of calculus. And I think the best way to go is just to write out something that makes a ton more sense. The definite integral from 2 to 1, the order doesn't really matter. You'll just see this is the easier way, of f prime of x dx is equal to f of 1 minus f of 2. Okay, and then I'll just keep f of 1 over here. F of 2 is 4, and then we'll leave the right-hand side. Let's see, antiderivative of 6x squared is some version of x cubed, and I'm pretty sure 2x cubed is the correct one. 3 times 2 is 6x squared, yeah. Minus x squared from x equals 2 to x equals 1. So f of 1, don't forget that 4, is going to be, let's see, 2 times 1 cubed minus 1 squared minus 2 times 2 cubed, so 16, minus 2 squared. So f of 1 is going to be 4 plus 2 minus 1 minus 16 plus 4. So let's see, what is that? So that's 10 minus 17, negative 7. Now we're getting somewhere. This graph really feels like a free response, released one. Let f be a differentiable function. The graph of f prime, the derivative of f is shown above and consists of a semicircle and 3 line segments. F of 2 is 3. What's f of negative 4? Okay, we'll come back to that graph in a second here. So we're going to do the definite integral from 2 to negative 4 of f prime of x dx is equal to f of negative 4 minus f of 2. Okay, this is kind of fun. I don't know, you and I have different versions of fun because we have to do fundamental theorem here by doing area under a curve. Let's replace f of 2 with 3. Okay, and so let's see, we're starting at 2 and going backwards to negative 4. So this, let's see, 2 wide, this is an area of 1. We'll worry about the signs in a second there. And that's half a circle, so that's pi times a radius of 2 squared over 2. And that's 4 pi over 2. Okay, so 2 pi. Okay, so the definite integral from negative 4 to 2, the semicircle would be negative, but we're going right to left, so everything looks opposite. So that's going to be negative 1 plus 2 pi. The negative 1, the heights are positive, and the widths are negative, so that counts as a negative 1 area. For the semicircle, for these representative rectangles, all the widths are negative, the heights are negative, The whole area we're going to count as positive in this case. Okay, f of negative 4 down below, add 3 is going to be 2 plus 2 pi. All right, feeling good. All right, this is the last one. And technically, this is substitution, but you folks can figure it out, I know. So if we're doing an antiderivative, we know that involves cosine. The derivative of cosine is negative sine, so this has to be a negative cosine. Don't forget your plus c. Let's put that in right now. And doing derivatives, the derivative of cosine of something is negative sine of that same something, so there's still going to be a 4 here. And if we did the derivative, we'd multiply by 4, so we need a division by 4 to balance everything out, and it looks like C is our answer.